All right, so here we are with our second video of gas law type things. And we're going to start with looking at the connection between the molar mass of a gas and the ideal gas equation. So we know the ideal gas equation, right? Our PIV-NERT here, PV equals nRT, or we can rearrange it to be number of moles over volume is equal to pressure divided by RT, right? That we all see how that happened, I hope. Now, if you remember that in math, you can always do this, that whatever you do to one side of the equation, you have to do to the other, no matter what you do. And so it is perfectly legitimate to multiply both sides of the equation by the molecular mass of a compound, which gives you this, right? Where we have the pressure times molecular mass divided by the constant times temperature is equal to moles times molecular mass over volume. Now, here's the thing. If we multiply moles times molecular mass, hopefully you know that this will equal grams, right? And grams, or mass divided by volume, hopefully at this point you know, is equal to density, right? And so if we, let's bring this back up here. So if we cancel this out and say that that is our density, right? So the density is equal to pressure times molecular mass divided by gas constant times temperature. And we can rearrange this here, as you just saw a second ago, to solve for the molecular mass of a gas using the density, the ideal gas constant, and the temperature, as well as the pressure, right? And so those are things that we can do. So now it is example time. And if we look at this, we can say, what is the density of carbon monoxide at a pressure of 5 atmospheres and 78 Celsius? So the first thing, right, we remember that we have density. Oh, that's a B. There we go. Density is equal to pressure times molecular mass over RT, right? We back up here. Density, pressure times molecular mass over RT. So first things first here, right? 78 Celsius is in Kelvin, 351. Right, we have our 5 atmospheres of pressure, carbon monoxide, CO2, and the molecular mass of that is about 44. And so now we have all of our information that we need, right? Because we know R is equal to 0.08206 liter atmospheres per mole Kelvin. That will cancel out the things that we need. We will end up with grams and liters. So then we put things in our equation. We have 5 atmospheres times 44 grams per mole. That's a really bad G. Divided by 0.08206 liter atmospheres per mole Kelvin times 351 Kelvin. And when we do this math, we get 7.64 grams per liter, right? Because those are the two units that are not canceling out. Grams don't cancel out, liters don't cancel out, right? So that would be the density of carbon monoxide. Now, what if we asked a flask with volume of 2.187 liters is filled with 3.74 grams of an unknown gas at a pressure of 754 millimeters of mercury at a temperature of 20 Celsius. What is the molar mass of this gas? If we go back, right, we can use this equation. The molar mass is equal to the density times RT over P. So we write this down, M equals dirt over pressure, right? But we have some converting to do first. All right, this is 293 Kelvin. We need to convert this to atmospheres. So we divide that by 760 because that's how we convert. So we have 0.98 atmospheres. And we start putting numbers in here. Oh, wait, and we need to figure out our density, right? These two numbers will give us our density, right? Because density is mass per volume. So we need 3.74 grams per 2.187 liters. Gives us a density of 1.71 grams per liter. All right, so now we can start putting numbers in here. 1.71 grams per liter times 0.08206 liter atmospheres per mole Kelvin times 293 Kelvin divided by our 0.98 atmospheres, right? The things that are not canceling out here are our grams and our moles. Look at that, grams per mole. We have the units that we want for molecular mass. And then we do our math here. And that would come out to about 42 grams per mole. And so that would be the molecular mass of this gas. So that is how you use the ideal gas equation in conjunction with molecular mass and density to solve some problems. Okay, so kinetic molecular theory of gases. So this is kind of the ideas that the ideal gas equation is built on and how we define ideal gases. So what it is a set of assumptions about gases that allow us to predict their behavior under ideal conditions. So the first one is that gases are composed of a large number of particles and they're in constant random motion. I think we can all be okay with that assumption. And then we have to assume that the volume of the particles that make up a gas are negligible compared to the total volume of the gas, which basically means we consider the atoms or molecules of a gas to have no volume. I don't know if we're all okay with that, but it's an assumption that we make. The third one, the particles that make up the gas do not exert attractive or repulsive forces on each other, which basically means we have to assume that the particles in a gas don't interact with each other. Also, I'm not sure if we're okay with that one, but it is the assumption that we make for the ideal gas. And then the last one, that the average kinetic energy of the particles is defined by the temperature and does not change with time or as a result of collisions between the particles, which basically means that we treat any collisions between particles as perfectly elastic, meaning that their energy does not change as a result of it, and that the temperature remains constant over time. So that is the last assumption that we make. Now, those are assumptions. Those do not hold true at all, ever. But they are good enough that under most conditions, we don't have to worry about deviation from those assumptions. However, at really high pressures, because once you put a lot of pressure on something, the molecules are going to be close together. They are going to interact with each other. They are going to see each other. And so we cannot make those assumptions anymore. Or at very low temperatures, because they don't have a lot of energy anymore, and so their collisions, we can't assume that they are perfectly elastic, and we cannot assume that they don't interact with each other when they do collide, and so we can no longer make that assumption, meaning that at high pressure and low temperature, those conditions create a non-ideal situation, and we can no longer assume that gases behave ideally. But luckily, we have an equation, the van der Waals equation, that accounts for these things and will allow us to make corrections based on deviations from ideal behavior. So what we have in here, you may notice it looks a lot like the ideal gas equation, except that we have A and B, which are van der Waals constants that you will look up in a table. You are not expected to memorize those. They will be given to you. And if you would really like to see one, look on page 418 of your book. There's a chart of them there. Now, example time. Yes, I'll pause for a moment here. Okay, if you are done cheering now and are ready to go through this example, we have 5 moles of an ideal gas at 0 degrees Celsius in a 22.4 liter vessel, and this should have a pressure of 5 atmospheres if this gas follows ideal behavior. However, we're going to say it does not because it does not. And so now we're going to ask, what is the pressure of carbon tetrachloride when accounting for this non-ideal behavior? So we've got our equation here, right? That's what it looks like, but we're going to rearrange it so that we are solving for pressure. Now that we have rearranged our equation, we are going to start putting some numbers in, right? We're going to take a look at the table in the back of our book, or actually on page 418, and we are going to find these as our van der Waals constants for carbon tetrachloride. And then we're going to fill in our numbers, right? We have our number of moles, our volume, our number of moles again, one of our van der Waals constants, our temperature converted to Kelvin, our value for R, our other van der Waals constant here, again, our moles, and our volume, right? So these are represented in several different places. We just plug them all into the equation, and after some strenuous mathing here, we find that we have a pressure of 4.14 atmospheres. Congratulations, we have now figured out the actual pressure of 5 moles of carbon tetrachloride at 0 Celsius in a 22.4 liter vessel. I bet you never thought you would know that, but here we are. Okay, last thing we're going to talk about here, effusion and diffusion. So diffusion, hopefully you are familiar with that at this point in your life, but here is a definition for it: the rate at which one substance spreads through a space or another substance. All right, like I say here, think of the smell of cooking pizza spreading from the cafeteria out into the rest of the school building on pizza days. The second term here, effusion, this is a very specific term, and it is the escape of gas molecules through a tiny hole. I bet you didn't know we had a special term for that, but we do, and it's effusion. And there are some equations that go with all of this, because it is all about how fast the molecules are moving. And so the first equation we have here is a root mean square speed of the molecules, which depends on their molecular mass and the temperature. We have an equation for the most probable speed of a gas, which also depends on the molecular mass and the temperature. And we have the average speed, which again depends on the molecular mass and the temperature. And so from these three equations, you may be able to tell that as a gas heats up, it's going to move faster because the numerator term increases in size. As the molecules of the gas get heavier, though, it's going to move slower because the molecular mass, or the denominator of our fraction, will increase in size. So, heavier molecules move slower, hotter molecules move faster. And for this, right, temperature is always in Kelvin. The value of R here, because we are dealing with energy, is joules per mole Kelvin, and M is molecular mass. So there's a guy, Graham, he wrote a law dealing with effusion that says the rate of effusion of a gas is inversely proportional to the square root of its molecular mass, which we just saw in the previous examples. Therefore, the ratio of the rates for two gases is equal to the square root of the ratio of their molar masses. Right here. This is what he is saying. So, the square root of their molecular masses, right, is equal to the ratio of the two gases, or their rate of effusion, right? But inversely proportional, right? You'll notice M2 is over here, R2 is over here. Inversely proportional. And so that concludes our notes on gas laws. I will see you in class.